All right, in chapter 3, we're going to review chemical compounds. We'll talk specifically about ionic compounds and move to discussing covalent compounds. So let's go ahead and get started. So first of all, whenever you're talking about this ion, an ion represents a charged form of an atom. Now, metals, which we learned about in Unit 1, tend to form compounds with nonmetals, which are also part of the groups we found about in Unit 1. Now, alkali metals, found in Group 1A, which is found on the first column of the periodic table, tend to react with halogens, found in Group 7A. Now, these bond to make a variety of compounds that feature very similar properties. In these cases, the two elements are always found in a 1-to-1 ratio, and characteristically, their compounds end up having melting points well over 500 degrees Celsius. Each represents a stable, white, crystalline solid, and in most cases, they're soluble in water and able to conduct electricity. Usually when I mention their capacity for electricity, I also take the time to mention this concept of electrolytes. Now, the electricity can only flow through a medium containing charged particles that are free to move. And so even though these guys are bonded together, when they're suspended in aqueous media, meaning you put these materials in water, they can have the ability to generate electricity. Atoms are electrically neutral because they contain equal numbers of protons and electrons. So there's no more electrons or less kind of thing. Now, in the process of their interactions, they cause the transfer of these electrons. And this means that by gaining or losing electrons, an atom can be converted into a charged particle called an ion. Now, an ion can form one of two kinds of ions, either a cation or an anion. Now, the loss of one or more electrons from a neutral atom gives a positively charged ion called a cation. And the gaining of one or more electrons results in that neutral atom becoming more negatively charged, and thus it is called an anion. Usually when I reference cations and anions, I reference this drawing of a cat called Plessy the cat, to think of it as a positively charged ion. And I refer to anion as kind of a girl drawing a sad girl named Anne, to reference the concept of anion. Now the symbol for cation is written by adding a positive charge as a superscript, and that usually indicates it's positive. You can write a number if there's more than one. However, if you just write a positive plus sign, that seems to be enough if there's only a positive one charge, meaning it has lost one electron. Now, for an anion, the symbol is a negative charge in the superscript. And unless there's more than one, the negative sign is sufficient in the superscript position. So again, to recap, for both the anion and the cation, when it's positive or negatively charged, if there's greater than one electron loss or gain, you'll want to use a number to go along with that sign. Now, halogens gain electrons the easiest of groups. Alkali metals lose electrons most easily. If you look at kind of the way they're placed on the periodic table, that would suggest that the elements found on the left hand side, featuring columns 1 and columns 2, have a higher propensity for losing electrons, whereas the ones on the right are biased and they tend to gain electrons. Now, noble gases are unique in the fact that they neither lose nor gain electrons, and thus that kind of fits their nomenclature or their epitaph of being labeled the inert noble gases. They tend not to react. Now, elements near the middle of the periodic table do not form ions easily. Elements that lose an electron and those that gain an electron will react with each other by transferring these electrons. In each case, the product that results is electrically neutral. Because opposite electric charges attract each other, this means positive and negative ions tend to attract each other, they are held together by an ionic bond. Now, an ionic bond, while strong, is essentially a force of attraction. We usually label this an electrostatic interaction. Compounds of these types are referred to as ionic compounds. Now, ions in ionic solid are held rigidly in place by attraction to their neighbors. Once an ionic solid is dissolved in water, the ions can move freely, which accounts for the electrical conductivity of these compounds in solution, and thus my reference earlier of electrolytes. As also highlighted earlier, the ionic compounds that are formed tend to display very high melting as well as high boiling points. For instance, sodium chloride, represented NaCl, melts at 801 degrees Celsius and boils at 1413 degrees Celsius. Now, ionic compounds dissolve in water readily if the attraction between the water and the ions overcomes the attraction of the ions for one another. Not all, but most ionic compounds tend to be water soluble. If you recall from our study about electron configuration, you can see how these groupings are set up. Alkali metals have a single valence electron, and thus their electron configuration is represented by NS1, where N is just the row or whatnot that they're found on, or what energy level, specifically from the off-ball stuff that we mentioned before. Now, halogens have 7 valence electrons, and their electron configuration would be represented by the figure there, where it's just a general scheme and can easily be replaced by the energy levels that represent where it's located. When halogens and alkali metals react, an electron is transferred, giving both NS2 NP6, which configures to achieve 8 valence electrons. Now, this word valence just means outer shell of an atom. And so if you picture an atom as having a central nucleus with protons in the center and neutrons in the center, the electrons are free floating on the outside, and the electrons found on the outermost level represent those valence or available electrons for reaction. Now, in all cases, these main group elements that have been mentioned, whether it's group 1, 2, moving on to the column that features boron, carbon's column, nitrogen's column, oxygen, fluorine, and so forth, all want to achieve octet. Now, octet rule refers to the tendency to undergo reactions that leave them with 8 valence electrons. And so what that suggests is that during the interaction of various elements, they react with one another so that the transfer puts them in a position where they have 8 electrons on their outermost shell. And that's the preferred arrangement of the atoms, where their entire outer shell is filled with those 8 electrons. For clarity's sake, if you look at the figure above, we have column 1A, and their tendency is they're going to lose 1 electron to become stable. If we look at column 2A, they'll tend to lose 2 electrons. And when they lose these electrons, they become these charged ion species. Looking on the left, the atoms, hydrogen, lithium, sodium, potassium, they become charged when they lose the electron, and thus the plus superscript designation. Likewise with beryllium, magnesium, and calcium, they have the 2+ designation, indicating that they have lost 2 electrons. Now, the transition metals are a little bit more variated in the sense that there are certain groups that exhibit the ability to either lose two or even three electrons depending on the nature of their interaction. And those exceptions are going to be chromium and iron. Now looking at group 3A, 3A features aluminum, and aluminum is going to lose 3 electrons to become cationic. Remember, cations are nothing short of just positively charged ion. Now if we look at group 4A, there's nothing really denoted because generally they have kind of their own program or regimen that they follow. And the same argument can be made regarding 5A. Now if you look at group 6A and group 7A, group 6A will certainly acquire 2 electrons. Now in this process of becoming 2 electrons, they are prone to becoming anions. The 2 indicates that they've lost the 2 electrons. They have gained the 2 electrons. And so if you're looking at oxygen, sulfur, and selenium, that's why the -2 charge is evidenced. There they have 2 more electrons, and in this process they're able to achieve octet. Looking further to the right, if you look at fluorine and chlorine, they exhibit the same movement of electrons where they gain 1. And thus they have the minus sign evidence that they are now filled with their octet of electrons, but now they are charged and therefore anionic. Now, when writing kind of half reactions of ions, you can represent that distribution in a number of ways. Here the designation is kind of written now based on the groupings that we talked about. If you look at group 1A, M just represents the metal in question, and anything in that column would be written as not M necessarily, but just the element itself without any kind of superscripts written. For example, if you wrote sodium, it would say Na, and then to the right you'd have an arrow that would say Na+, and then to the right of it you notice this E figure, which means electron, and that just shows how the sodium neutral atom becomes the sodium cation, which now has an available electron that can later be reacted. If you look at group 2A, the same tendency is observed. You have a group 2 metal such as beryllium, Be, that when it becomes a cation, it forms Be2+, and thus the 2 electrons are represented by 2E- to indicate that you have these 2 available electrons. Looking at group 3A, the trend is again followed. You have aluminum. It yields aluminum 3+ with 3 electrons available for reaction. And then if you look at group 4A and 5A, they tend to kind of have that ambiguity that I mentioned, so we really don't lean on their tendencies of how they form octet because it varies. It's not as straightforward as the others. Now if you look at group 6A, 6A is going to be your group that features oxygen. And if you see the difference, in groups 1A, 2A, and 3A, you notice that the electrons located on the right side of the actual balanced setup, whereas on 6, as well as 7, if you will, the electrons are shown to be on the left-hand side of a reaction scheme. Now, what that displays on group 6A and 7A is simply that they are neutral atoms that are interacting with these electrons to become these anionic or negatively charged species. So group 6A reacts to receive 2 electrons, forming its anion. Same thing with group 7A, it forms an anion as well. And so it brings about this description that I mentioned earlier, where your transition metals form cations but can lose 1 or more d electrons in addition to losing valence s electrons. Now, that's just kind of an exception or kind of a statement of fact, but what you really want to take home from this particular slide is just the overall scheme or behavior of the electrons transfer when you're talking about cations versus anions. Some general points from the ion formation, and I think I'm already mentioned them, but I'll reiterate them. Metals form cations by losing one or more electrons. If you look at group 1A and 2A metals, they form +1 and +2 ions respectively to achieve the noble gas conformation. Noble gas conformation is another term colloquial with octet, or they're synonymous with one another. Transition metals can form cations of more than one charge by losing a combination of valence shell S electrons and inner shell D electrons. While that's a good point, the overall scheme of what you should take from that is definitely the first item from that bullet point when we're talking about group 1A and 2A metals. Now, reactive nonmetals, found on the right-hand side of the periodic table, form anions by gaining one or more electrons to achieve the noble gas configuration. You have group 6A nonmetals that feature oxygen and sulfur, and they form anions, as I highlighted earlier. And then you have your group 7A elements, the halogens, which form ions by gaining one electron. And again, the group 8A elements are unreactive, inert, thus they are the noble gases. Now, as far as the behavior, the ionic charges of main group elements can be predicted using the group number as well as the octet rule. So use that to decide how the trend of an atom is going to behave when forming an ion. As I highlighted, group 1 will lose one electron, group 2 will lose 2 electrons, so forth and so on. So you want to keep that in mind. Now, this is not necessarily directly related, but salt is an ionic compound, and usually I take the time to mention how much it is important that salt consumption is highly regulated. There's a recommended dose for the average adult, and it varies based on your demographics. And so you want to keep that in mind as you ingest or imbibe any type of food source, because generally speaking, salt is found in a number of items. And so it's very important that you monitor it because it does have impact on blood pressure, i.e. hypertension, etc. So moving on, naming ions. This is not as heavily focused as just making it known. The main group metal cations in groups 1A and 2A and 3 are named by identifying the metal followed by the word ion. So for all intents and purposes, when you name something from those columns, it'll just be sodium ion, calcium ion, boron ion. And these are the elements that form cations. And so you just name them the respective element name followed by the word ion. And that's the easiest way for labeling those types of charged atoms. So as I mentioned, you have your cations. Now, however, when you have your anions, it's a little bit different. For cations, it's just the ion designation at the end. But on ions, you have to replace the ending of the element name with the IDE or IDE followed by the word ion. For instance, if you were looking at fluorine and it became an anion, it would be dubbed fluoride ion. Or if you had sulfur, it would become sulfide ion. Now, polyatomic ions are simply put atoms that are more than one, that are consistent of more than one atom. The atoms in a polyatomic ion are held together by covalent bonds. Now, a polyatomic atom or ion is charged because it contains a total number of electrons that is different from the sum total number of protons in the combined atoms. This encourages a net charge. Now, these atoms are encountered so frequently that it almost becomes essential to memorize their names and formulas. However, for the intended purposes here, it's just set up for you to familiarize yourself and shouldn't be something that should necessarily be memorized at this point. Here is a listing of those polyatomic ions, and this is just kind of a snapshot of some of them. Some of them are very common, and you may see one or two of those later, especially the hydronium and hydroxide ions. Hydronium is very important when we start discussing pH, acids, and bases, and as is hydroxide. So that's the list of those ions. And this is just some external information regarding the behavior of ions. Now, one characteristic thing that you want to note is that whenever you read over literature talking about having elements or essential vitamins or things of that nature, most of these elements do not occur naturally in nature, meaning that if you have a neutral compound of calcium, it probably was obtained experimentally or from some kind of scientific purchase. As a feature in our everyday world, calcium actually exists as an ion, and whenever people are referring to it, whether it's calcium-rich bones or calcium for tooth structure, they're actually referring to the calcium ion. Now, all chemical compounds are neutral. Once the ions are identified, you can decide how many ions of each type give the total charge of 0. Now, the chemical formula of an ionic compound will tell you the ratio of anions and cations, and that's when you're just looking at kind of a chemical formula. And you'll look at more specific examples of that later on when you see actual ionic compounds. Now, just as kind of a scope of what that means is when they're forming the compounds, you have calcium plus, which is a cation, and you have fluorine, which is an anion. And when they come together, they form potassium fluoride. Notice I said potassium, and then I labeled it fluoride. Fluoride's on the right. I labeled it last with fluoride on the end. And fluoride as opposed to fluorine because you have the IDE designation. Now, if the ions have different charges, unequal numbers of anions and cations must combine to have a net charge of 0. So if you look at these examples, you have calcium plus and oxygen 2 minus. They go through this charge balancing thing, which charge balancing essentially is just in a colloquial term. There's a more colloquial term called drop and swap. If you notice, the charges in the superscript essentially switch rows in the subscript. The 2 from the oxygen goes down to the subscript of the potassium, and that +1 becomes just a regular 1 in front of oxygen. Likewise, if you look at the calcium 2 plus and the 2Cl of the chlorine, you end up with calcium and Cl2. And again, highlighting what I mentioned, there's the charges, although being able to do this is not as dire as one would imagine when it comes down to identifying compounds. Now, the formula of an ionic compound shows the lowest possible ratio of atoms and is known as a simplest formula. There's no such thing as a single neutral particle of an ionic compound, and a formula unit identifies the smallest neutral unit of an ionic compound. Once the number and kinds of ions in a compound are known, the formula can be written using a list of rules. This list first includes what you name in the cation first and the anion second, which I kind of mentioned earlier. You do not write the charges of the ions, and then you use parentheses around the polyatomic ion formula if it has a subscript. And that helps with just understanding how to interpret what they look like. Now, these compounds are named by citing first cations and then the ion with a space between the words. There are 2 kinds of ionic compounds that contain cations and main group elements, and then there's ionic compounds that contain metals that exhibit more than one charge. Sometimes these require different naming conventions, which we won't really venture into because it's part of that. If you memorize the polyatomic ions, it would make it a little bit more of a complex arrangement. So these are the type 1 examples, just so you can see them. And these are type 2 ionic compounds. And it's just for clarity's sake to see examples. You won't be tasked with naming compounds at this juncture, so it's more of a familiarity strategy to encourage you to kind of review and just know what they look like. All right, so do not use these kind of names for compounds like this. It will never be iron dichloride or iron trichloride, especially with those kind of ionic compounds. You don't need to do that. And these are some additional names of ionic compounds, just to get an idea of what they look like. Now, part of the naming is going to come from familiarity of just being made aware of compounds. And then, honestly, in most cases, you'll see the chemical formula to accompany the chemical name unless there's a specific reason that you're being given the chemical formula and not the name. And that concludes our lesson for today on ions. And we have discussed both the positively charged and the negatively charged ions and how they become those particular types of ions. So